Today we are going to solve this integral using again substitution. This substitution in this case, let's say u, will be t. It is the variable that we want to substitute, and we will apply the root square of c over b. This is a trick that we used in the previous video. Let's use it again. So here, if we pass this to the other side, we have u square root of bc. See that I switched the order here. It is possible, right? Because this over t. Basically what I did was u over square root of c over b. This square root is all this way, and I can put this on the top, but I have to invert the order, and we will have that. Okay, so if we have already that, what will be the dt, right? So in this case dt will be, this part is the same, square root of b over c by du. Okay, and what else? I can also calculate the t square will be b over c u square. Okay, so I remove the square root. I can also calculate what will be to have b plus c times t square, right? In this case, what will be this expression? I can write that as b plus c that multiply b c u square, right? And we can get rid of the c, and we will have finally b, because we have to be here, that multiplies to 1 plus u square. And the square of this also, let's say if we want to continue here, let's say we have ct square, right, square. This will be equal to everything that we have in this part to the square, right? b square that multiply to 1 plus u square square, right? Then what? Then we have to include what we have inside of the integral with the new variables, and then we will do the substitution also of the variables, or the variable limits. So we have t square dt, right, over b plus c t times t square square. We said from this calculation that t squared will be b over c u squared multiplied by the derivative, which is square root of b c by the u, okay, over everything that we have squared, which is this one, b squared 1 plus u squared, right? So we can have this part, this part, and this part, and this part outside of the equation. So I have the exponent 2 here, and we have no exponent in this part, but we also have an exponent and a half in this place. So if we do the math, we will have this is 1, this is 1.5, and this is minus 2. So we will have 3/2. Okay, will be, and C also we have 1/2 here, and we have 1 and 1.5 here. This is 3.5, and because it will be minus exponent, we put it outside. Okay, over we have this one and this one, u square times the u, the v square, we keep it this for now, 1 plus u squared over 2, right? Now we can do the, okay, we can, I think we can factorize this one and this one. If I remove it, this is 1.5, right? 1.5, and if I remove it, and this is minus 2, 1.5 minus 2, we will have a 0.5 negative, right? So we will have something like this, 1 over b 1.5, c 3.5. Okay, if we see here, we go from 0 to infinity, and the variables that we have here are linear related, so we will also have the limits from 0 to infinity of u squared by the u over 1 plus u squared square. Okay, now what? We can again doing another substitution. Let's say u is tangent of theta, right? And the u is the secant squared of theta by a derivative of theta. And we also know that 1 plus u squared is the secant square of theta, right? This is an identity. Everyone knows that. I will include another identity here, maybe that u square, and this is not an identity, it's just squaring the u is tangent square of theta, right? So now what? Now we have this part. Let's get this part alone for a minute. Okay, and we have this that is going from 0 to infinity, from u squared the u, 1 plus u squared squared. This is equal to, now the limits will go from 0 to infinity. In here 0, tangent 0 is 0, but infinity will be in p and a half, right? Pi and a half. So this is how the Greek said it, but in English is pi. Okay. And we will have tangent squared, right, multiplied by du. Du is secant squared of theta by the theta. Okay, and below we'll have this part squared twice, so we will have secant 4 of theta, which is the same of 0 pi 2, and then I can cancel 2 from here and these 2, and I will have the tangent theta by the theta and secant square of the theta, right? And this is the same. This is the same to have from 0 to pi 2, pi and a half of okay, tangent, let's put tangent square of theta, and second is the inverse of the cosine, so you see cosine square of theta. Okay, let's write it better. I mean, and let's put this here. Tangent is sine over cosine, right? So if I have from 0 to pi 2 sine square, right? Or then cosine square over theta multiplied by this cosine sine square, right, by the theta, we can get rid of this and we will have an easier integral, which is sine square of theta by the theta. Now what? How can we solve this? Let's apply another substitution. 0 pi over 2 is equal, sine square of theta is the same as 1 minus cosine square theta by the theta, right? And this is 1.5 of theta, because if I do this, is theta here, minus 1.5. I already did this substitution in another time, and this is not a square, I'm sorry, this is the double angle. Okay, so if I substitute this to theta, I will have to put the half of, because the derivative of theta will be the half sine of 2 theta. Okay, from 0 to pi and a half. And in this case, from sine, if I put 0 here, it will be 0. If I put a pi and a half, we will cancel the 2, and sine of pi is 0 also. So this part is 0, right? This is the only part that will go from 0 to pi and a half, and 0 is 0, and pi and a half is the only one that we will keep. So we will have a half by pi and a half minus 0. Okay, and this is the same of 1/4 pi. So if we combine this solution with this part that we have from the beginning, the solution will be 1b and a half c 3.5, right, by pi 4. Okay, let's write this in a different way. Basically, this is pi 4 square root of b c 3.5, and that is the solution, considering that b and c are constant. Okay, thank you.